Hey guys, so we're going to look at rules of differentiation specifically to logarithmic and natural exponents here. So we'll begin with this bell work. All right, so always a good idea to pause the video and quickly try this if you haven't already done so, and then we'll do it together. So if we're tackling this one, the best thing is always, of course, think of this as actually being to the power of 1/3. And so then when we're taking the derivative, of course, we get 1/3 times 9x squared plus 4 to the power of negative 2/3. And then we need to multiply it by the derivative of the inside, which is simply 18x. And I can simplify that as well, although I can't access my tool. So let me just move this a little bit for a second. Maybe we'll put it on that side. Okay, and so then I can simplify this 18 over 3 to just be a 6. Okay, and then what I'm going to do is put this on the bottom. So on top, I've got 6x. We're going to cross the line and flip the sign for this. So it becomes 9x squared plus 4. All of that is squared. And of course, that means cubed root when we've got that third. So g prime of x is actually going to be this. A little bit sloppy, but you can see it. And then, of course, what we're doing, though, is finding the tangent line. So that means we need our pot and sot. So over here is going to be our pot. We're almost done with the sot, or slope of tangents. Let's do that. Find g prime of 1. That's going to be 6 over, let's see, 9 times 1 squared is 9, plus 4 is 13, squared is 169, cubed rooted, which does not simplify. So that's going to be our sot. And then our pot is going to be 1, and we plug 1 into this equation here. So we get the cubed root of 13. So last thing then is to actually write our line. So y minus the cubed root of 13 is going to be equal to our slope, which is 6 over the cubed root of 169. That's really hard to read. Let's clean that up a bit. 169 times x minus our x coordinate. And that would be our tangent line, or the equation of our tangent line there. All right, I'm going to put all right, looks like I'm going to have to leave myself on the bottom right there. I was hoping to move it, but not possible. All right, so we're going to look at our differential rule then for natural exponential functions. So our d dx, specifically of e to the power of f of x, so some other function, is just going to be f prime of x times the original function, so e to the f of x. So we kind of love this one because it's super easy, right? Like this is not at all in any way difficult. We take the derivative of the exponent, bring it down, and slap in the original function, and we're done. So let's put that into some practice here. So for this one, right, we're going to take the derivative of that exponent, which is cosine of x, and we're going to just put in the original function, e to the sine of x. So as you can see, super easy. Do the same thing over here. So the derivative of our exponent is 2, and then we put in the original function again. And so on and so forth. A little bit trickier if we've already got a coefficient, but all it means is that the derivative is 2, and we multiply it by that existing coefficient to get the 6, e to the 2x. Now, this one over here is a little bit more complicated. Let's see if we can figure out why. Hopefully you said that it's a product rule, right? We got two different things multiplied. So that means I'm going to take the derivative of the first times the second function plus the first function, make sure you got brackets around it there, times the derivative of the second, which is 3e to the 3x. So nice and easy for us. Here we're going to have a little bit more complicated product rule. So this time we're going to end up with 2x e to the 2x plus our first function, x squared, times the derivative of the exponent, which is 2, and then the original function, 2x. Now, the other thing that I would say is usually here we're going to put our numbers at the beginning. So I'm going to change this to 2x squared e to the 2x like that. Okay. Now, for our next one here, this one is going to be a chain rule mixed with it. So first we're going to take the derivative of like our chain rule, right? So the outside function, which is simply something square rooted. So we've got this 2e to the 2x minus 6, and that's to the power of negative 1/2. Then we need to multiply it by the derivative of what's inside there, which is going to be 2 e to the 2x minus 6. Now, we don't really like writing it like this. This is pretty sloppy, pretty ugly. We don't like those negative exponents. So first of all, we've got a 2 over 2. So we're going to get rid of those. And then we're going to leave what's on the numerator there. So e to the 2x minus 6. And I'm going to put it over top of our this one, making it like cross the line and flip the sign, right? Make that positive. So e to the 2x minus 6 all rooted. Now, you may see this if you rationalize the denominator, or you can just see it without it, that this is the same as like e to the 2x minus 6 rooted squared. So what we could do is just write it exactly like that. And this could be our answer as well, okay? Particularly if we're rationalizing the denominator, but yeah, those are both correct. All right, so one more example here. Of course, we did a product rule, we did a chain rule. Let's take a look at it when we combine it with a quotient rule here. So this is where we're going to use our low d high minus high d low. So low d high, derivative of the high function. It's kind of an ugly e, there we go. Minus high d low, so e to the 5x times 6x, all over low squared. Okay, then we can simplify those out. So here we've got a 15x squared e to the 5x, and I'm just combining my coefficients here. We're going to put the coefficient first, just because that's how we're used to seeing it. And then, of course, this one, if we square it, is going to be 9x to the 4th. But you'll notice I can take a 3 out of every single one of those coefficients, so I'm going to do that and get 5. Over here, I'm going to get a -2, and I'm going to put it over 3. Now, I didn't write the rest of it yet because if you look, we can also take out an x out of all of those terms. So that would leave us with x e to the 5x, and this would leave us with e to the 5x. On the bottom, we end up with, not x to the 4th, sorry, x cubed, right? And so that would be our final solution there. All right, that's pretty much it. It's not hard, as we said. So the next thing we want to do is we want to look at our differentiation rule for natural logarithms. So this is if we have d dx of the ln of f of x, okay, where there's a function inside of that natural logarithm. So if we've got that, that means that we're going to get f prime of x, so the derivative of what's inside the logarithm, over the original thing that was inside the logarithm. Okay, so again, this is, as you can see, pretty easy here. So let's apply this to a few examples. So this one, the derivative of what's inside is simply going to be 2. So I get 2 over the original 2x minus 3. This one's a little bit more complicated, but it is going to follow that same pattern. So the derivative is 6x plus 2, and I'm going to put it over 3x squared plus 2x. Nothing I can really do to simplify that, so we leave it at that. Okay. Here we've got it with trig, no different. Right, we're going to take the derivative of cosine, which is going to be negative sine x, over our original argument, which is cos x. Now, you'll probably never seen it left that way because, of course, this is negative tangent of x, because we got sine over cosine there. All right. Now, this one's a little bit more complicated because you can see here, not only are we doing a natural logarithm, but we've got a chain rule in there as well. So let's work this one out here. We're going to take the derivative of what's inside, which means we've got 1/2 times 2x minus 4 to the power of negative 1/2 multiplied by the derivative of what's inside, so 2, all over the original argument, 2x minus 4. Now, obviously, we don't want to leave it that way. Let's start by simplifying those 2's. And then, really, we probably shouldn't leave it like that. So if this is 1 over the square root of 2x minus 4, and this is also that, that is effectively just going to be 1 over the square root of 2x minus 4 times 1 over the square root of 2x minus 4, which is actually, we can combine those and just get 2x minus 4. Now, if you skip this middle step and you can see that this goes directly to the bottom, there is nothing wrong with that, right? If you're good with algebra, go ahead and skip some of those simple simplification steps. Wow, that was hard. All right. So let's try applying this now. What we're going to do is use our calculator. So you might have to pause it quite a bit through here because what we're going to do is practice using our calculator. I'm not going to explain how to do that. I'm going to assume you either know how or that you can or do it in class with me. Okay. So if we do this, what I'm doing is I'm trying to find the derivative of this function at -2. So I'm going to give that to you, but you're going to use your calculator to do it. It's a little bit different for each calculator, which is part of the reason why I'm not going to explain it on the video. Okay, we've already had some videos about that, and we've done it in class, or you already know. So then what we want to do is we want to just look at what is it doing? Is f of x increasing, decreasing, horizontal or vertical tangents? Well, if the derivative is negative, that tells us that f of -2 is going to be decreasing. And it's decreasing because remember, we always want to give our reasons in calculus, because f prime of -2 is less than 0. So it tells us it's decreasing. If you take a look at this next one here, I'll give it to you. Same function, but different value. I just realized too, this is not x. That is -2. All right, so f of 1, I've got it written down here already for us, 11.268. This is positive. This tells us that f of 1 is increasing. And it's increasing because f prime of 1 is positive. All right. Now we're going to switch it up, have a little bit different function here, do some trig for us. Okay. And again, you can see these are a little more complicated, which is part of why we're using our calculator, right? A lot of what we do in calc, particularly our first calc class, we need to use the calculator. Later on, we learn all the techniques and ways to do it, but especially beginning, granted, we could do these by hand, but we're learning to use the calculator. So f prime of pi over 3 here is going to be equal to -0.372. Now, because that's negative, what does that tell us? Well, it tells us that f of pi over 3, or f of x at pi over 3, if you prefer, is decreasing. And it is decreasing because f prime of pi over 3 is less than 0. Remember, that's always our reasoning, right? Is we want to make sure we include that. So in this case, derivative's negative, original function is decreasing. Try it again here. This one is going to tell us that f prime of pi is undefined. Now, if it is undefined, does that mean it's a vertical or horizontal tangent? Horizontal tangent, right? We learned that that is when it is a slope of 0, or hopefully you learned that in pre-calc stuff. And then, of course, for a vertical one, well, our run is 0, so we're dividing by 0 on that slope. So what this tells us is that we're going to have a vertical tangent. So f of x at x equals pi has a vertical tangent. Okay, that's going straight up or down. All right, so then next one here, we're going to look at this. So we've got a kind of an awkward function there, but it's actually really easy if we think about it, because it's just going to be a chain rule as we pull it down, e to the original function. But we're using our calculator, so when we plug this in, f prime of 0 is going to be 0.340. That is positive. So f of 0 is going to be increasing because f prime of 0 is positive. And for our last example here, we're going to plug in, we got a new function again, f prime of 1. Again, we're using our calculator. We're going to find that that is 0. If it is 0, this means it's a horizontal tangent, because now we have a slope of 0, right? We've got an infinite run over a rise of 0. So this means that f of 1, so let's say should be has a horizontal tangent. All right. And it's got that horizontal tangent because, of course, it's, like I said, the run is infinite, but the rise is 0. So 0 divided by anything is just 0. All right, so let's take a look at this next one. When the value of the derivative of a function is positive, we know it's increasing, the original function. When the derivative is negative, the function is decreasing. When we speak of quantities increasing or decreasing, they do so at a certain rate. They do it faster or slower. We already understand that the derivative is the slope of the tangent line. Okay, slope is a rate. Right? You've done this in physics or science class. You've also probably, hopefully, done it in your algebra classes. Therefore, the derivative of a function actually represents the rate at which a function is actually changing. So here, if we've got the number of people entering a concert, can be modeled by this function, where t represents the number of hours after we've opened the gates. Then we want to know, what is the value of f of a half and f prime of a half. Using correct units, explain what these represent. So let's start off with the non-derivative one. So f of 1/2. This just means that if we plugged in 1/2 here, well, it basically already tells us this is the number of people entering into the concert. So I'm going to type this because I think it'll be a little bit easier for you to read. All right, so we'll go like that. And so this is the number of people entering the concert 30 minutes after the gates open. 30 minutes because it is f of a half and the t is measured in hours. Okay, then let's find out what f prime of 1/2. And you'll notice here, I'm not giving us an answer yet. What we're doing so far is just coming up with what does this actually represent? What does it mean? Because I find that's often more helpful for us. If we know what it means, it's a lot easier to find the answer and understand it. So this is the derivative. So this is how fast this is happening. So this means that 30 minutes after the gates open, oops, there we go, open, there is an increase of let's say a number of people per hour. I realize it's a little bit awkward if we don't have the number, so we'll edit this slightly after we get them. So once again here, we can do this in our calculator, like we just learned. So if I just plug in 1/2 for this, I'm going to get the answer 904.482, which tells us there's 904 people entering the concert 30 minutes after the gates open. Now, after that half an hour, we want to know what it's changing by, and it's 793.757, again, by using the derivative at a point on our calculator. And so we get this. Okay. Now, first of all, we're going to need to change these a little bit. We can't really have all these decimals, right? So this one is going to be 904 people. Oops. People per hour, right? And then this one is going to be 794 people per hour, but this is increasing, right? So it's a little bit different because as we can see, there is an increase of, and instead of number, we can actually say 794 people per hour. So it's not that there are 794 people entering, but it is getting 794 people per hour faster than it was previously. Now, the one thing you will notice too is like I rounded this one up. There's a good argument that this should be rounded down because we can't actually have 0.7 of a person. And so the only full number of people is 793. I think in this case, you can make an argument for either because we are also obviously estimating these things. All right, how many people have entered the concert 2 hours after our gates are opened? So what this means is we need to know f of 2, right? Because we want to know how many people we're entering after. And so this is that there are 1390 people entering. And again, we're going to use our calculator and just plug in 2 for that. So there are this many people entering. Okay, and f prime of 2, okay, we want to know, like, is this thing like going faster, slower, what, right? So f prime of 2 here, this is going to be, again, we're going to plug it in, derivative at a point, and we're going to get negative 578.5. I'm going to leave it at 578 then because we can't have half a person. And what this means is that because f prime of 2 is less than 0, that's going to tell us that the number of people entering is decreasing. All right. And so what it's just telling us, which makes sense, 2 hours after the gates have opened, we would imagine that there are less people because most of the people have already arrived. We also know how many people are currently entering our concert, right? Because it tells us the number of people entering the concert is that original function up here. Okay. So that's how many people are entering per hour. Okay. I just realized this question is actually worded wrong too. Now that I look at it, how many people have entered the concert? It should be how many people are entering. Because if we say have entered, that actually requires us to do some integration, and we don't know that yet. So we'll come back to a question like that later. All right, so let's take a look at another one. After being poured into a cup, coffee cools so that its temperature, T of t, is represented by the function T of t is equal to 70 plus 110 e to the negative t over 2, where t is measured in minutes and T of t is measured in degrees Fahrenheit. So what is the temperature of the coffee 5 minutes after it's been poured? So this is just using our actual T of t. So T of, and in this case, we're going to find 5, and you're just putting 5 into this equation up here, okay? So if you do that on your calculator, you'll get 79.029 degrees Fahrenheit, which I would probably round that to just 79 degrees Fahrenheit, all right? Now, is the temperature decreasing faster 1 minute after it's poured or 3 minutes after it's poured? So what we need to do then is compare the rates. So let's find T prime of 1 and T prime of 3. And we need to see what are these rates so that we can, analyze them. So T prime of 1, again, we're just going to use our calculators and find the derivative of this function at 1, okay? If we do that, our calculator is going to tell us that it's negative 33.359 degrees Fahrenheit. And now that we've derived, it's going to be per minute. At 3 minutes, we get, and the same thing, find the derivative at 3. So you can use your calculator and find the derivative of this at 3, or you could find the derivative by hand and then plug in 3. But since we're using our calculators right now, we're going to do it that way. This will be negative 12.272, and again, degrees Fahrenheit per minute. So what does that tell us? Well, that means that it's actually decreasing a lot faster at this point, right? Here, it's only decreasing by 12 degrees Fahrenheit a minute, whereas at the beginning, after 1 minute, it's really hot. So, of course, if you've, again, taken some science or physics, we know that it's dissipating or diffusing into the air much faster. So that heat is being conducted out into the colder air. And so what this means is that the temperature is decreasing faster at, sorry, not capital T, lowercase, time is 1, then T equals 3. And our reason is because, now we could look at this in the, like an absolute value way of kind of saying like the absolute value of T prime of 1 is greater than the absolute value of T prime of 3. Now, you don't have to use these absolute values. You can use context to understand that they're cooling, so the temperature has to be negative. And because that number is more negative, or in other words, has a steeper slope, it's going to be doing it faster. So that conducts this lesson, guys. I'll see y'all shortly for 3.5.